Hello, welcome everyone to a new Tech at Lunch session, special on energy and cost reduction. My name is Edward Kikken, and I'm here with my co-workers, colleagues from UGent, Kurt Stokman, and Stijn de Rammelare from U Antwerp, and we're going to have a talk on energy optimal motion trajectories. Before we dive into the technical topics, maybe a small, let's say, explanation on how the IT infrastructure works for this. So the cameras and microphones of all participants are muted by default during the presentations, but you can post your questions in the Q&A chat box, and we'll answer those at the end of the presentation, as far as we have time. We'll also record this event and share it at a later moment, so please don't make your own recordings, use the ones we make. On those notes, let's dive in. Maybe a bit of a high-level introduction. So basically, the challenge that we're trying to tackle here, it starts with the world today. We have global warming, increasing energy costs. Therefore, there is a global drive towards increased sustainability and a reduction in energy usage. And in this presentation, we tackle, of course, only a small topic in this large field. And the idea is to focus on energy reduction in industrial machinery by improving the motion, so the trajectories at which we run these machines. To make it nice and concrete, we developed a little example case based on a SCARA robot. So it's a parallel, let's say, robot. The task that we used for this presentation is simply to pick an object in point A and move it through whatever trajectory, can be a straight line, can be something curved, to point B. So a pick and place operation. We are looking at the optimal trajectory to go there, and we're going to use tracking control to follow the trajectory. So we're not looking at torques to the motors, but we're just prescribing a Cartesian XY trajectory. The goal is then to go from A to B in a certain target time and minimize the energy that we need to actually achieve this task. To give you a little teaser, we know by the end of this presentation, you will see that we can reduce the energy for these kind of tasks by at least 30%, and in some cases a lot more, compared to a conventional trajectory approach. So there are actually large gains to be had by the approaches that we are going to propose here. Maybe for comparison, talk quickly about the conventional approach for these kind of pick and place robotics applications, but actually something that is often done for most motion systems. It's basically plot a straight line from A to B, then try to run at a constant speed for as much of that area as you can, and limiting the initial acceleration around A and the final deceleration around B. Again, using tracking control. So everybody's intuition for these kind of cases is that reducing the speed and the accelerations and decelerations will reduce the energy in these kind of situations. But actually the mapping from the limits that you use on speed and acceleration to the used energy is rather complex. And an additional degree of freedom that you're not exploiting yet here is that a non-straight path, so let's say some sort of curved path, which might be more ideal given the kinematics of the robot, might reduce energy even further. So, okay, we know that a conventional approach is maybe not the best way to do it, but then what do we propose? How do we propose to improve this? A very high level idea is basically we're going to use a model that predicts the energy for a given trajectory. So assume we have some model of our machinery, of our robot, of our whatever kind of motion machinery we have. We're going to use an optimizer to basically vary the points along this trajectory. And then we're going to iterate between using the model to evaluate the energy and using the optimizer to optimizing the trajectory to basically find a minimum energy trajectory formulated, well, visually depicted here. So basically looping over the two to basically optimize the trajectory to minimize our energy. This can be formulated as an optimal control problem. It's basically the control theory way of solving these kind of cases. It's important to know that for complex cases, so complicated machinery, complicated dynamic systems, these OCPs, so optimal control problems, are really non-trivial to solve. But Flanders Make and UGent, U Antwerp have tools to actually help you in this process. So nowadays we can solve these kind of problems for a wide class of systems. In this presentation, we're basically have a bit of a split. So I'm going to present the case for which you have dynamic models of your system. So let's say this can be MATLAB Simscape models, they can be Modelica models, they can be handwritten models. Typically, these are kinematic relations, dynamic relations, differential equations. But the alternative approach that's going to be presented by Kurt and Stijn is when you start with a CAD model of your system. So you don't have to rely on these dynamic models. You can use a CAD model and actually derive the kind of dynamics behind it. Both of our approaches are going to lead to this optimal control problem formulation, and both will lead to energy optimal trajectories. So there's multiple paths that lead to Rome here. Diving in on my part of the presentation, so using the dynamic models, that's what we'll do first. So basically, we have made at Flanders Make some tooling to make this kind of approach easy. At the beginning, we already identified that basically interfacing with the models that you have is a challenge. But if you can use intuitive modeling environments, for example, Simscape or Modelica, you basically take away a lot of the problems of formulating these models, make it a lot easier, less time consuming for users to get up to speed and up and running with these things. To know the MATLAB toolchain that we're using is actually based on Casadi. It's a toolbox, a package developed by the DMMS group at Flanders Make, so part of KU Leuven, that uses, let's say, an intelligent way to analyze the equations you give it, and you can combine it with sort of powerful state-of-the-art optimizers to actually solve complicated systems, where previously, historically, this would only work for very simple, trivial systems. Nowadays, with this Casadi workflow that we have, we can actually solve way more advanced systems, way more complicated models. An interesting note to make about all of these approaches is actually that typically we will do an offline computation of the trajectory. So we have our model of our system, we know what the tasks need to do, and we know it doesn't change in time or as a function of environment. So basically you can pre-compute the optimal motion trajectory and it doesn't need to change in time. However, sometimes in more complicated environments, the task may change, the system itself may change, or the environment in which the system operates varies, which actually needs then an online adaptation of the trajectory. Think about, for example, more autonomous vehicle scenarios. You need to, let's say, dodge a pedestrian. I made a little table here to sort of, let's say, clarify this a bit. So basically, when we do the offline trajectory computation, this is really the, let's say, clear OCP case. The complexity to deploy the trajectory that you find is actually very low. You can put this kind of thing in a lookup table and you can run it on any kind of PLC or industrial controller. There is really no additional challenge once you solve the offline problem. And then the energy optimality that you achieve is actually good. It's even perfect if your model is perfect. But that is only for a given task with a perfect model and also a fixed environment. So when we go to these online adaptation trajectories, we can use multiple techniques there: model predictive control, MPC, iterative learning control, ILC, and many more. Typically, the computational cost, so the complexity to deploy it, increases a lot. You need to write a rather complex tooling at this point to make this work. So really an ongoing topic at Flanders Make is really to make these toolings easier to use and to reduce the computational cost, to make these things a lot more user-friendly and usable in an industrial setting. And that will allow us to actually achieve energy optimality in, let's say, varying task system environment and be a lot more robust to imperfect models, which is also a limitation. Now, considering that we're still hard at work on the right column, I'm going to present some examples on the middle column, which is the offline computed trajectory, and show that already gives you very nice advantages for these kind of fixed problem structures. First, back to the original example that I used on one of the first slides, is this SCARA pick and place robot, where the conventional trajectory that I showed was actually a straight line, A to B, with a certain speed profile that I omitted here for simplicity. But the RMS torque that we need, and that RMS torque is actually, let's say, tightly coupled to the energy you need, is 56 Newton meters, so it's rather high. And then we run it through our optimization approach using a dynamic model of this robotic system, and we can reduce it from to 36 Newton meters. And you see actually that this kind of curved path, it's really exploited. It's captured by the model, and the optimizer will find this kind of reductions when they are possible. Basically, this means that we can get a 36% reduction in the RMS torque, which should at least lead to an energy loss of that size, probably even more. So really interesting gains are to be had here. Another example that we recently worked on was a Delta robot. So that's actually the three-dimensional version, a more complicated version of a parallel robot. And here maybe the plots are a bit too detailed, but the main numbers you need to be interested in is actually that the conventional trajectory uses 123 RMS torque, and we can reduce that to only 77, which actually is quite a similar reduction to the SCARA case. So the RMS torque will go down by 37%, and energy losses should be reduced by at least that. I believe brings me to the end. I have a little video here because videos are fun. So some more application areas that we have used our tools, because actually one of the powerful things about this tool is that funny, thanks Kurt, is that it's actually widely usable. So anytime you have a dynamic model of your system, so it can be, as I said before, Modelica, Simscape, whatever, you can run these kind of optimizations to get more optimized control signals. So we used it in hybrid electric vehicles, in cam follower designs, even in compressor network controls. What is it? This is energy management for, what is it, grid solutions. For CBAT project, which does battery management, magnetic springs, which are tools we can add on top of mechanical systems. So really there's like a very broad and wide range in which we can use this tooling that we have developed. I think that brings me to the end of my part of the presentation, and I would give the word to Kurt now to talk a bit about the CAD-based approach.
Thank you, Edward. Hello, everybody. Indeed, as Edward has shown, if you have a good analytical model of your system, then you can immediately run those optimization tools. But in many cases, you don't always have those detailed analytical models. Are you then stuck? Well, no. We also developed another approach in which we can use indeed a CAD model. As an application, you can see here a movie of a cold forming process, which is a high-speed application where we have to move pieces in 24 milliseconds. It's also an A to B, point-to-point application. And this mechanism is a rather varying system. It's a crankshaft mechanism with an inertia profile with changes, and that inertia profile must be known is key in optimizing the energy consumption of this motion application. In this application, it's also possible that the masses that you move are changing. If you have another product running in that application, you also want to know this impact of mass change. So let's see how we dealt with this. Trying to go to the next slide.
Is the control working for you, Kurt, or should I do it?
Yeah, perhaps it's not working. So if you could click.
Yeah, no problem.
Yeah, thank you. So here you can see both the real machine in the lab and the CAD model, which is a pretty good simulation of the real system. And if you have your CAD model, most applications do allow to CAD applications do allow to add motion to that. And based on that, you can easily reveal the torque and speed relations of such an application and the inertia profile. For the case here, you can see in the middle that the inertia changes by a factor of 17 between two extreme positions. So it's a big change in inertia. If you have that information about your torque speed relation and inertia profile, you can also tune your controllers, as you can see on the left bottom figure, where we have a simulating schematic with some feed forward based on that information that we gained from the CAD models. Those control schemes can immediately be downloaded into your commercial drives to have your system operating. Another thing that we have worked on is the next slide, in which we also have the opportunity to use that information from a CAD model to have a reduced model, which allows us in this case to have an identification of the change of inertia if we run different products on the machine. And as you can see, in the middle you have two sinusoidal curves which actually show that during operation of the machine we can track the varying inertia, and this then again can be used in what we call, which is an online optimization of your trajectory. And as Edward was already saying, we are still working on the implementation of such online trajectory optimizations to be commercially used. So with this information at hand about inertia torque, then you can start with the motion optimization, trajectory optimization, and Stijn will explain how we do that at Ghent and Antwerp.
Yes, indeed. Thank you, Edward and Kurt. So if you have indeed this inertia variation,
Horen jullie Stijn nog?
I cannot hear Stijn at this point. I was assuming it was on my hand, but maybe not then.
no. Normally you should hear me now.
Yes, we can hear you.
Okay, sorry for that.
Yes.
So if you are a machine builder, you probably want that your machine moves from point A to B in a certain time, but how the speed and the acceleration profile in between looks, that's mostly free. And so there we have an optimization potential. And on the next slide, we should be able to see that we have these normal position profiles, like here on the left, the standard position profile. We see that there are many torque components in that total torque. We have friction, we have changes of inertia, we have acceleration. And on the next click, we will see the optimized motion profile. So we obtain the same position delta and the same time delta, but now we can do this with a much lower torque because the optimizer shifts different torque components apart from each other. Therefore, we have a smarter dosing of our acceleration, and in that way, we can reduce the amount of energy a lot. On the next slide, you can see how we translate this into a motion profile optimization tool, which allows to optimize this motion profile based on the load torque and inertia that you may have obtained from CAD profiles. So at the Flanders Make at U Antwerp Core Lab, we designed a motion profile optimization tool that's completely possible to run in Excel. So every company most probably already has the necessary software tools to run this optimization. You can also easily get that Excel motion profile optimization tool by just sending me an email. The email addresses will be available at the end of the presentation. What is important is that the potential that you obtain with these optimization tools are in many cases better than the things you obtain with standard state-of-the-art optimizers. Because we heavily focused at obtaining the global optimum, we see that in some cases this can be a substantial difference from the standard state-of-the-art optimizers. So this is all available in our Excel tool, with which you can freely play. On the next slide, then we see again a measured optimization potential. So in this case, the Netsroof case that Kurt explained, we see that we can obtain energy reduction of 62.9% with this optimized position profile. So nothing changed to the machine, nothing changed to the motor, nothing changed to the drive. The only thing that we had to adapt was the motion profile. And by adapting that motion profile, the machine running in the field could run with 62.9% reduction in energy. That was, in short, my message.
I think that brings us to the last slide of this presentation, capturing some main sort of takeaways, the main message that we're trying to convey here. And that's basically that there is a sizable reduction of energy consumption possible compared to the sort of conventional approaches, really like large numbers, double-digit percentages that are possible. And it's also good to remember that the tools we have shown here are very broadly applicable, so a lot broader than the cases we have shown here, but given limited time, we had to focus on a few. And we have did our best to make them as user-friendly as possible. Remember that you basically need a model of the system. It can be some handwritten Simscape Modelica or even just a CAD model as presented in the last slide. And we're mostly working, let's say the tools are ready for fixed trajectories, but we are working on the adaptive version of this. And I think we all expect to get interesting results of that in the coming months and years. What can we offer as the Flanders Make network? So Flanders Make Intramuros, but also the U Antwerp and the UGent Core Labs. Basically a wide set of tools and expertise in this kind of energy optimal motion, let's say optimizations. Do contact us if you want more information. I've listed the email addresses here. Don't hesitate, send us an email, contact the Flanders Make offices, and we can talk about your cases. Finally, a small heads up, the next session on energy optimal, the tech at lunch for energy optimal things is about upgrading legacy machines to enable the kind of supervisory energy control. It's going to be with my colleague Ted Ooyevaar. It's going to be on the 28th of November. Also call in there to see what's going on in these kind of topics. I think that's about it. So back to you, Steppe, I guess.
Yes, for the Q&A, we have one question so far. Reducing energy means also increasing execution time and as a consequence, decreasing productivity. So what is the best trade-off?
I think that's a very relevant question. The case I've shown in Netsroof, there we took the execution time as a constraint for the optimizer. So in that case, actually, the execution time we obtained with 62.9% less energy was exactly the same as the original execution time. Of course, if you start increasing the possible execution time, your energy, you will be able to reduce the energy demand even further. But in this case, the numbers that we projected here were a case where the execution time was exactly the same as for the benchmark. And I guess that Edward can also talk on that on his case.
Yeah, so indeed, on the cases that we ran, so the SCARA and the Delta robot, we also used the execution time actually as a constraint. So the time we took to move from A to B was actually the same in the conventional and in the optimized approach. We really exploit, let's say, other degrees of freedom than making the whole process slower. Yeah. And get these kind of, quite interesting gains there.
Just to add, in the Netsroof case, indeed, we were able to reduce the energy. You may have noticed that the RMS and maximum torque values that are required have been reduced. So this also opens other insights for that application. You can, if you want to maintain the timing that you have now in the application, you could actually run this machine with a smaller motor. Or if you use the same motor, you could also think about speeding up your process. So the insights that we gained in optimizing the profiles, the motion profiles, also opens perspective for new designs of that same machine.
Okay, thank you everyone for the clear explanation. We have no more questions so far. Maybe we should wait a couple of more seconds, but if there are no more questions coming up, then we can wrap up this session. Okay, we have been 3 to 4 minutes in Q&A now, so there are no more questions coming up. So I'll leave the floor to Edward to close this session.
Well, I guess I don't have too much to say about this. Thanks a lot for the question that we got. Thanks all for calling in, and I hope it was clear and informative. And again, do contact us if you have needs in these kind of energy optimizations, or if you just want to have a technical chat to see what's possible for your application. and enjoy the rest of your lunch.